There we go. So this way you can, if you miss class or if you want to go back and review something that you missed, you can easily do that. They're up on YouTube. They're unlisted. You just have to go to my website, click, but it's just a YouTube thing, so it'll work on anything. So you do have access to that at all times. And actually, if you go back, you can look at my old classes lessons as well. So that's not what I wanted to do. So what happens when I try to use the touchscreen? All right. So let's finish going through the syllabus now. Grading is pretty straightforward and simple. It's 4 tests and a final exam. So each of your tests is 15% of your grade. The final exam is 30% of your grade. And then there's 10% per participation. As long as you come to class on a regular basis and show up and don't sit there and just sleep, you get the 10%. All right, that's just my fudge factor. So I have a little bit of things because I've had a couple times where students would just literally show up for the tests and think they were going to pass. And that's kind of that's my little fudge factor. So as long as you come to class on a regular basis, you're getting the 10 points. It's very rare that I ever take any 10 points away from anybody. So each of the tests, we will have a review class the day before the test. So the Tuesday will be, if you have a test, it'll be on Thursday. The Tuesday class will be the review for that test. You'll also have the review test up online, so you can practice it and see there. The answers will also be up there for the review test. So, and then the actual test is that Thursday, and it's basically the same type of things, just different numbers and stuff like that from the review test. So it should not be too difficult to do. The final exam is a cumulative final exam. It will be, I think it's on May 11th, if I remember right. Might be the 12th. Nope, May 11th. So, and the tests and everything else are already on the syllabus. As long as there's no drastic things with snow and stuff like that, I pretty much will stick to the syllabus pretty well. So, are there any questions with that? I actually have this class, and then I have my next class isn't actually until 5 o'clock tonight. So I'm here all day. So if after class or anything else like that, if you need extra help or whatnot, I can go over certain things with that. I'll just literally be across the hall in the adjunct office anyway. So if you do want to come, or if you have a class after this, you want to meet in the afternoon, just let me know. So I will be here from 11 to 5 every day, basically allowing you guys to get extra help and stuff like that if you need help. My email address is there. Have anything, just email me. Like it could be at any time. It's like, okay, I'm going over this stuff on Saturday. It's like, I really don't get this. Just send me an email. I'm normally on my computer because my day job now is actually publishing. So I'm writing a book. So it's like, I'm literally at my computer anyway. So if I'm there, I'll respond back to your email pretty quickly. So that's probably the fastest way to get a hold of me is just to send me an email. All right. You'll notice that in the grades, there is no homework grade. I don't collect homework. The homework is on you. So every class that we go over, you do want to try the odd number problems on the book. The answers are in the back of the book. My test questions come from the questions in the book. So if you can do the odd number questions and get those all right, you'll be fine in the tests. If you can't, ask questions. So at the beginning of class, or if you want to come in a little bit early and you have some questions on the homework or anything else like that, ask, and I will go over those. The reason I don't do the homework is because it's hard for me to be able to get it back to you in time to actually have it make a difference, because we go pretty quickly. It's like we're basically doing a chapter a week. So by the time I get the homework back to you from chapter 1, we're probably going to be on the end of chapter 2, and it's just not going to be useful. So do the homework on your time. If you have any questions on it, feel free to ask, and I'll go over those. We will do quite a few problems in class too, so that's not going to be that big of a deal. The only actual day off we have is the spring break. Every other class period, there was no holidays or anything else that fell on a Tuesday or a Thursday this semester, so which comes out to be kind of nice. All right, let's see. Any other questions with the syllabus? Yes.
I have a good question. So how do we access your lectures through Google Classroom?
They're not in Google Classroom. It's on the website. So Baker's Math Class. Wherever it says website.
They might say they were recorded in Google Classroom.
They're recorded on Google Meet. I'm using basically this computer's not connected. I'm literally broadcasting it to Google Meet and then recording it. So it's just going to be when you click on it, you're going to see a Google Meet recording. So that's all I'm doing to record it. The other nice thing is actually, if for some reason you're sick or anything else like that and you cannot come to class, if you send me an email before, I can send you the link to the Google Meet and you can literally watch class at home. Okay? On the rare occasion that you just literally can't make it. So just send me an email before class and I can send you the link when we start class and you can join it that way. It's one of the nice things about using that. All right. So yeah, I can show you here. So basically, if you look at, like, this is from last semester. So this was the class, and it's like, and that's basically just click play, and that's the lecture that I was doing. So, so you could actually go back if you want to go back and look at some of my old lectures. Like, I might have explained something a little bit differently, or they might have asked a question that you didn't think of asking during the class. You can easily go back and look at it. It's always going to be available to you. So, all right. So, your turn. How many of you guys is this your first math class at Three Rivers? The rest of you would take 095 and stuff like that? Okay. Not a problem. It's funny. Last semester when I taught this class, this was the class, for some strange reason, like half the class was math phobic and hated math. So is it the same this time? Not great math people? It's fine. It's totally okay. I totally understand it. I've done this for a long time, and yep, math just isn't one of those things that people like. One of the things that I want you guys to understand about this class is it's different. So this is not a traditional algebra class. All right. This is not like your 95 class. This is not like 137. All right. There's going to be some formulas, but the vast majority of it is going to be understanding what they're talking about and interpreting information. All right. That's what statistics is. All right. It's actually probably one of the few classes that is completely used every day. We use statistics for everything. So one of the things that I'm going to do when we're going through and explaining things, and I'm talking about different things, is I'm going to connect it to stuff that you see on a regular basis. We just had the election back in November, and it's like you saw polling data, you saw polls online. That's all statistics. Like, they don't ask every single person in the country what they're going to vote for when they put up the poll. They're asking about 1,000 people. And they're saying with those 1,000 people, they can determine what everybody is basically thinking. Okay? That's using statistics. And what I want to get from this class is understanding how that stuff is used, how they come up with that stuff, and how I like to call statistics the only class or the only math class you can lie with. All right? When you get data, you can manipulate the data to show what you want to show, and using it to the information to basically convince other people that you were right with the same data that somebody else is going to convince people that you're wrong. Okay, so that's literally where statistics comes in. I taught high school for 23 years. I've heard every single stupid, dumb question you could possibly think of. Okay, so if you have a question, ask. Don't be afraid to ask a question. Because if you have a question, I guarantee half the class has the same question and there's the same thing. Okay, so just ask it and we'll be able to go through and explain it. I've got plenty of time built into the schedule, so like it's not going to totally throw off the schedule. We're not going to get through stuff. Okay, so that's that little thing. We're going to look at some of just the basics of statistics today. We're not going to go into anything crazy. Oh, calculator. You do not necessarily need a calculator. Most of the stuff that we're going to use, if you have a cell phone, you can download Desmos. The Desmos Scientific Calculator will work fine. There is certain times where I'm going to tell you literally we're going to go to Google and type in this calculator and use this calculator online. All right, that's totally acceptable. So because one of the things that I think some math teachers have a problem with this, but it's like when you're going to use it outside of this class, or if you're ever going to do this outside of class, you're going to use Google. It's like that's just the way it's going to happen. You're going to search something, you're going to find information. Okay. So I don't necessarily, my questions and stuff aren't designed in a way that you're going to literally be able to look in Google and find the answers. But being able to go online and find some information to be able to help you with that, that's fine. Okay. So that's why you don't necessarily need a graphing calculator or a special calculator for this class. You'll be able to use your cell phones, no problem with that. Any questions with any of that? Does anybody know what statistics is outside of what I just said? Does anybody think they use anything like this in their job? What do you do?
I don't know.
Right.
So like what the company stats and stuff which we
Very good. Yep. So one of the things that we're going to talk about today is actually two different types of statistics: descriptive statistics and inferential statistics. Okay. So, and a lot of the stats stuff that we're going to look at today is, or actually in general, is vocabulary. It's a lot of terms and stuff that you've never heard of before and understand, but they're going to make sense. One of the things I like to tell people is mathematicians are lazy people. As crazy as it sounds, we don't want to make things harder than it has to be for us. So the words are just going to make sense because that's just the way they are. So if we're talking about, I'll switch over to it. Descriptive statistics. So descriptive statistics are describing something. So the example that you just gave for your job, those would be descriptive statistics because it's describing how the employee is working and how the store is doing. Most statistics that you guys have seen on a regular basis would be descriptive statistics. Okay. In high school, did you guys do anything with stats and data? Yeah. What kind of things? What's some examples? Yeah.
I did on like my favorite soccer team, and I did the statistics of the players scoring, how many goals or assists in the
Okay.
game.
Well, what did you use to figure out how it was? What goals per game? It was there was a word I'm looking for. Starts with an A.
Average machine.
Yeah. All right. Average. That's something that you guys use all the time. That's a descriptive statistic. It can actually be an inferential statistic too, depending on how we're looking at it. But typically, it's descriptive, and that's how you guys have mostly used it. So average, does anybody know the other name for average? Mean. Okay, so we've got mean. What are the other two that you learned at the same time? Mode and median. Okay, good. Mean, mode, and median. All right. Don't ask why we have two names for average. It doesn't make any sense to me either. I think they just wanted to make them all M's. So we have mean, mode, and median. All right. Mean and median actually both work with numbers, and you can use those with words or other kind of like how many red people, how many like red shirts, stuff like that. So you can actually use those. Mode is the only one that can actually have multiple answers. All right. So mean is average. Most people know what that is. What's median? The middle. So what is the first thing you have to do if you're going to look for the middle? Yes, they all have to be in order. That's very important when we're looking at things, is making sure things are put in order. What's mode?
The number that repeats the most.
Yep, the one that's most common. So it can be actually multiple ones. It's like if you have, so now it's mode's one of those weird ones. If everything appears once, there's no mode. If everything appears twice, there's no mode. However, if everything appears twice except for one number that appears once, all the rest of those are mode. All right. So it just can't be all of them, but it could be a subsection of all of them. So if I have two things that appear 4 times and everything else appears once, those 2 things that appear 4 times is my mode. Okay. What are some other things? So we talked about mean, mode, median. You've seen those before. What are some other ways that we can show data Charts and graphs. You ever heard the thing of pictures worth 1,000 words? We use graphs and charts and stuff like that all the time because it's easier for people to see what's going on. All right. Most people are scared of numbers. We talked about that at the beginning of class. Most people are scared of math. They're scared of numbers. However, if I put a pretty pie chart up there, it's like, ooh, I understand that. Because it's pretty, it's easy. There's no numbers necessarily on it. There might be numbers on the side, but you can look at the pie chart and get a ton of information from that pie chart. Now, remember I said math, statistics is the only thing you can lie with. That's how people manipulate you. Graphs can be deceptive. So I can actually take a graph that, actually, let me find one real quick. There we go. Oh, man. All right. So here's a graph. Which group does the best? Is Group A drastically better than the other two groups? Why?
2.5 off.
Okay, now you're looking at numbers. If somebody doesn't like numbers, they're just looking at the bars, right? Does this graph make it look like Group A is drastically better than Group B and C? Yeah. Okay, so that's where when we start to look at statistics and we start to look at how, now is the data wrong here? No. They have the graph, they have the numbers there to show you so the data is not wrong. So somebody could say, I'm not lying, the information's here. Okay, however, the information's skewed to make you believe something that might not necessarily be true. That's the same graph. Does it look the same? No, it looks drastically different. Same information, but now Group A doesn't seem that bad. That doesn't seem that far ahead.
The y-axis has different scaling.
Yeah, the y-axis
Then-
definitely has different
then-
scaling.
Than the one that you've shown. Than the one that you showed us.
Right. This is
Different
this is basically a broken graph. If it was done correctly, they should put a little break down the bottom, but they don't ever do that. But the data is exactly the same. And depending on what the person wants to convince you of, depends on what graph they're going to show you.
I didn't mean to interrupt.
No,
I
you're
had a
fine.
Question.
Yeah.
So, if we are making graphs, right? If a math problem in the book that you assigned to us were to like tell us to make a graph for something, can we use breaks in our graphs or no?
Depends on what the graph's asking you to do. Yes, you can use breaks. And I'm actually going to show you another one here. This is the same kind of concept. So here's a graph. It's got the data in it. Unlike the last one, is this one skewed? Nope, it's going from 0, right? So if we look at that one compared to this one, which one's a better graph? Why? Let's see if I can get them both on the screen.
Can't really tell where the first point is on the first one. It's just somewhere under 10.
So if I want to show that prices are staying pretty calm, pretty level. If I want to show you that inflation's horrible and the things are spiking, I want to show you this graph. That is the same. Your visualization, your information that you get from it is drastically different. Okay, so that's where you can start to see how people can manipulate things using the same type of information. So here's another one. This graph's looking at just a few months, where this graph's looking at many years. If you look at this graph, depending on what it's talking about, it's like, wow, things are going up a ton. You look at this graph, well, it's way better than it was 3 years ago. Even though it's going up those few months, it might not be necessarily going further out. So it's like we can start to look at those type of things. Pie charts. In all my years of school, in all my years of teaching, I swear administration has no idea how to use pie charts. Everybody loves pie charts. Pie charts are very specific things to be used only in certain situations. A pie chart has to equal 100%. Okay? The pies actually should meet and be accurate to the percentages that they represent. If we're looking at this one does not equal 100%. Okay? So it definitely changes your opinion on what you're looking at. It's like it doesn't give you an accurate representation of it. For some strange reason, everybody loves a pie chart. Don't know why. But these two graphs are showing the exact same thing, but this would be a lot more accurate representation of that type of data. You can use the pie chart, you just have to actually change it so that it's divided by 100. So like if you added up those percentages and divided them, you could get it so that it's out of 100 and still be an accurate representation. It's just you have to do that to actually use the pie chart. Oh, this one's actually kind of interesting too sometimes. You'll see this a lot in politics and stuff. Colorings. How we represent color, we start to see different things. So typically, when you're looking at sparse representations or you'd look for more light. If you're looking at darker, it'd be more dense. Things like that. So you can see that. The one that's, see if I can find it. Yeah. This is the sure. Who won? Red or blue?
But blue because
This is the presidential election map from 2020. But that's where you can start to look at it. It's like if you want to show, well, there's no way the Democrat could have won. Look at all the red. There's no way this is possible. All right. But the population for the United States, if you look at just this part here, then it's what is that part? Florida and then part of the coast of California. That population there is the exact same as the entire rest of the country. Okay? The majority of the population lives in the Northeast, the Southeast, and along the coast of California. So yes, there's a ton more red there, but almost nobody lives there. Okay. Wyoming has like 600,000 people in the entire state. Wyoming is this state right here. Connecticut has 5 times that. I drove out to Yellowstone over the summer, and you drive through Wyoming, there's nothing. Absolutely nothing. You drive for miles, and all you see is one house, and it's like, and then keep going. It's like, oh my God.
So basically, you just see barren landscape. So
Basically, yep, it's tumbleweeds and fields. There's nothing. We drove through 2 towns that were for sale, like the entire town. It was like, oh. But yeah, it's that's the problem. Like the majority of the population is not in this area. There's like nobody out there. So yes, there's lots of red there, but that's because there might only be a few thousand people in those counties. So, but that's how we can start using the information. And that's the one thing I really want to get you guys out of this class is that I want you to understand where the information's coming from, how to look at the actual data and the stuff that they're talking about behind the bullet points, and really see what it means, instead of just taking what they're telling you at face value. Okay, that's the important piece that we're going to get out of this class. So most of the stuff that we've talked about is descriptive statistics. Sports is a great use of descriptive statistics. Baseball, out of all the sports, baseball is the best predictor when we're looking at statistics because you have a lot more of the sample space. You have 162 games in a season. Where in football, I think it's 17 now. They upped it by one, I think. It used to be 16. So it's like we have more data in the sports worlds. So most stuff when you're looking about sports is descriptive. How many games they won? What was their batting average? Points per game, assists per game, things like that. I see all the time online. Facebook is crazy with their algorithm because they really recognize when you stop on things. So I'm a data person. I like data. And for some strange reason, apparently now they think that I really like LeBron James and I can't stand basketball. But they keep coming up with they're trying to compare him to Michael Jordan and which one's the greatest player of all time. And it's constantly destroying up statistics. And then they cherry pick certain statistics of each one and compare them. It's like, oh, look, this one's better or this one's better. And it's like, guys, you can't, it's like, there's no way to compare things like this. It's like, but they cherry pick the statistics to meet those needs. So, or in baseball, Shohei Ohtani is crazy. It's like he's pitching and hitting. It's like, it's absolutely insane what he's doing. Nobody's ever done it. So they're trying to say that he's the greatest pitcher of this generation. It's like, and they're cherry picking certain statistics that makes him better than everything else, but they're not looking at all of them. It's like, so that's where you start to look at, it's like, okay, let's look at the holistic thing. But all that's descriptive because it's all data that we have and we can look specifically at that data. There's a second type of statistics, one that the majority of you probably have not seen, but you're influenced by it all the time. It's inferential statistics. You'll notice I'm not an English teacher. I screw things up all the time, especially with spelling. So this is why I copy and paste. Inferential statistics. This is where we're going to look at samples or we're going to look at data that we're going to collect and we're going to infer something about the entire population. Okay. Now, with descriptive statistics, is that data accurate? Like if I'm going to look at the batting average of a baseball player or the points per game of a basketball player, is that data accurate? Yeah, because I'm looking at the actual data, right? Like it's already been collected, it's already happened, I have it. All right. So if I'm going to infer something, let's say I ask everybody in here their favorite color. And I get your favorite colors to be cyan. I'm just picking something random. Can I infer that the entire population of the school's favorite colors cyan? No.
You don't have any data to prove that influence.
But I collected it. I asked everybody in here.
I retract my earlier statement.
All right. So, but that's actually a very important thing. So when you're trying to infer something, remember at the beginning I said those polls that you saw online when they were talking about who's going to win the election or who's ahead or do you like this policy and things like that. They only ask about 1,000 to 2,000 people. Okay. How many of you guys have ever answered the phone for a pollster or a survey? Have you answered their questions? You did?
I don't remember it.
That's fine. Good job. There's a reason for that. Think about it. Like, if the majority of young people specifically, first of all, you rarely answer the phone unless you know who's calling. Okay. And if you answer the phone and you don't know who's calling, you're probably going to say you don't have time and hang up anyway, especially if it's somebody like that's going to ask you a bunch of questions. Who's the one type of person who is most likely to answer the phone and then take the time to answer a survey?
My grandma.
Yeah, your grandma. Like that's what it's called, old white people that have nothing better to do with their time, but they're sitting there and they're going to answer the questions. Okay, if I'm calling up 1,000 people nationwide to find out who they're voting for and who like what policies they like, that's who's going to answer those questions. So my data is going to be skewed. Like when I asked you guys, or I didn't ask you, but I assumed your favorite color is cyan. Your now favorite color is cyan, no matter whatever your favorite color is. So you make those assumptions based on the data that you collect. That's inferential statistics. Okay. If I do the same survey and I get a different group of people answer the questions, the stats should be similar, but they might not be exactly the same. Okay. If I can get one thing out of you guys by the end of the class, it's like when you get somebody calls you up and asks you a bunch of survey, answer the questions. As crazy as it sounds, take the 5 minutes to answer the questions. Because that data and that statistics and that information that they collect is used by companies, by politicians, by our government, everything to make decisions. And that was the one, so back in 2016, when Trump beat Hillary, it was like, they didn't understand why that happened. Like all the data, all the polls, everything else said Hillary Clinton was going to win. She didn't. Trump won. And what they found out afterwards was the vast majority of people they were calling did not want to state that they were going to vote for Trump on the phone. They didn't want to tell somebody else that they were voting for Trump because there was a negative connotation to the people who were voting for, and there still is. So they were less likely to vote for that, state that to a poll, and it threw off all the data, and that's why you saw something different than what ended up happening. And actually, the same thing even happened in 2020 with the polls. The polls were a lot further apart than the actual final election was. And the same thing happened. But unfortunately, there's very little ways for pollsters and stuff to get data instead of calling people. All right. So, or it's like an internet survey and stuff like that. You might get different results, but it's not scientific. And the thing that we're going to learn in the next class is how to actually come up with that type of information. How do we decide what type of people to ask? If I'm asking just you in here, I'm going to refer to the entire school. That doesn't work. You're not a random sample. Okay? If I do an internet survey or a poll online and just have random people answer it, again, the people who are more passionate about that cause on either side are the ones that are going to answer. The ones that are not as passionate aren't going to answer it, and those are the ones that you actually really want, because that's the data that you actually want. That's why I got a kick out of it. So I'm not a Democrat or Republican. I can't stand the two parties, but I try to listen to all the candidates. And almost every poll online in 2020 had Joe Jorgensen, who was a Libertarian candidate, winning the election. This was never going to happen. Like, as much as I would have liked to see not a Democrat or Republican win, it was never going to happen. But all the polls showed it. I think she got like less than 2% of the vote. It's because the people who are going, like, they would send it out in groups and they would just bomb the poll with their opinions, and it would skew those results. And then people took that results and ran with it. Okay, so it's like you got to start looking at those type of things. So in inferential statistics, we have two main pieces of information, or two definitions that we need to know: population and sample. Population is the entire thing. whatever we're talking about. So if I'm looking at the favorite color of the school, the populations of the school. The sample is the people I asked. And that's got to be a subset, a randomized subset of that group. All right, so here is the 1948 presidential election. Is this a descriptive statistics or an inferential statistics?
Descriptive statistics.
Why? Why?
The data's right there.
Yep. And is that all the data? Or is that a piece of the data? That's all. There wasn't that many people. The 1948 population was a lot smaller.
So there's all the data basically.
Yes, that's all the data. So yes. So that would be a descriptive statistics. All the data is there. What would be the best way to display that data in a chart?
Bar graph.
Do a bar graph. You actually could do a pie chart with this one
For that.
because it adds up to 100%. Your percentages add up to 100. So you could actually do a pie chart with this one. But a bar chart would be fine too. Actually, a bar chart and a pie, those two is the problem is you're going to see, because you have to really go all the way up. These two numbers are pretty close. So that when you show it, even on a bar chart or a pie chart, it's not going to be as much of a spread between those two. So that's why you start to use skewed graphs. It's like, I might not show these three people on my graph. I might just show those and do a little, so you can see the difference between it. And if I was Truman, I would show the graph that shows a lot bigger between the two of us than if I was Dewey. And if you know anything about presidential elections, this was the election that the newspapers called for Dewey. And on the front page of every newspaper in the country, the day after the election was Dewey wins the presidency. And then he did when all the rest of the information was counted. So it's like everybody says, well, we always used to know who won the elections the day of the election. No, we didn't. That's more of a new thing. And actually, even at that point, it's literally the media using inferential statistics to determine that. They have pollsters go out to the polling stations and ask exit polls. Who'd you vote for? Why'd you vote for them? Those type of things. In all my years of voting, I've never seen one. Apparently, they just don't really care about Connecticut. But they get that information, and then based on their understanding what happens typically in the areas and where those votes come in, they can predict who's going to win before all the votes are in. Unless strange things happen, which is like what happened here, or what happened in 2000 with Bush and Gore in Florida, or what happened in 2016, or what happened even in 2020. And even actually last year in November, there was quite a few of the Senate races and stuff like that that went literally down to the wire, and they couldn't predict them until all the votes were counted. So most times we do not know officially who won the presidency or any election on the night of the election. They actually have 2 weeks to certify the vote. So that's when they actually officially, all the votes are counted and we know who actually won those things. And sometimes it can be different. There was a couple of votes in Connecticut that actually were won by less than 10 votes. I think there was one in the state that was won by a vote. So it can make a difference when we actually go through and count them all. All right, testing baseballs. Do we have any baseball fans in the house? Okay, a couple. For the past couple of years, we've had like 1 year it was like constantly hitting home runs. It was like the ball was just flying. And then all of a sudden something happened and the ball was dying. They changed the baseball. They literally changed the baseball. So, morning.
Sorry.
That's okay.
Statistics.
Yeah, the syllabus is right back there. I didn't actually grab them if you want to grab one.
Thanks.
No problem. So if we're going to be testing baseball, so it says early in the 1977, pitchers began to complain that the ball was livelier than the Spalding ball. So they collected data for the first 616 games. 1,033 home runs were hit. And then only 762 were hit in the last 616 games. So the data that we just got there, is that descriptive or inferential? That's descriptive. We have actual data, right? Okay. Sports Illustrated sponsored a study of this. In this study, an independent testing company randomly selected 85 baseballs from the current 1977 supply of various major league teams and measured bounce, weight, hardness, and compared them to similar tests in previous years. Is that descriptive or inferential? That's inferential. We took a completely random sample of the balls, not all of them. We only took 85. Okay, and then we compared it back. The conclusion was the 1977 Ron's ball is livelier than the 1976 Spalding, but not as lively as it could be under the rules. So it was more lively, but not necessarily drastically livelier than those other balls. So that's the difference between descriptive and inferential. Okay. So other thing that we can look at, there's two different types of studies or experiments or things that we can do. Now, these are all, whenever you're doing these are going to be inferential statistics. Okay, because we're not looking at all the data, we're going to cherry pick and look at a randomized selection of it. So an observational study is one where we're observing some characteristics and taking measurements. That'd be like a sample survey for it. Most things that you have interacted with have been observational studies. The surveys, asking questions, pollsters, all those are observational. Even though we're asking questions, it's observational because we're getting that. It's what you think back. If we're looking at the baseballs, that was in one way it could be an observational study because we're looking at that. In another way, we're going to talk about the next one is a designed experiment. All right, the next one is a designed experiment. This is where researchers impose treatments and controls. All right, so most of your medical type things, vaccines, medicines, drugs, things like that, are designed experiments where you have a control group, you have a testing group. It could be a blind study, it could be a double blind, those things you hear when you talk about, those are designed experiments. And we're observing what's happening and we're taking measurements and then we're going to infer information from those. 2020, the pandemic hit, coronavirus hit. We're still actually living with that. We're going to be living it forever. It's the flu is literally from 1918. The actual Spanish flu that we got in 1918, the flu we're dealing with today is the same flu. So coronavirus is going to be around for, it's just going to be like the flu at that point. The studies that came out in the beginning when they were starting to investigate the vaccine, do you think those were observational studies or designed experiments? Huh? Designed experiments, okay. So when they first were doing the studies for the vaccine, they had to get volunteers, right? So people had to volunteer to take this vaccine that nobody had ever seen before. Okay? So that part is definitely a designed experiment. However, there's one big piece that a design experiment has to have. It has to have a control group. Okay? The control group has to, one, assume they're getting the exact same vaccine. and two, act no different than they would have acted otherwise. Okay? That's the big difference. And that's the one thing that changes some of the initial tests from a designed experiment to an observational study. Their control groups change their behavior based on what they got. So if you want to see if a vaccine is going to work, you want both groups to do the exact same thing. And if you now know you're protected or you think you're protected, some people were taking less precautions, might not have been wearing their mask properly, might have been going out more often, things like that. In some studies, however, the other thing was true. It's that both groups were completely locked down and couldn't do anything. So you were never going to be exposed, even if you didn't have the vaccine and then if you had the vaccine. And that corrupted a lot of data because they didn't have that control or that all the they had too much control over the actual information in that situation. So that changes that data and how we can actually use that information. So they originally thought they were a lot more effective than they were because these people were doing all the other precautions at the same time. So was it the vaccine that was keeping them protected, or was it the mask wearing that was keeping them protected, or was it them being locked down that was keeping them protected? It's like it was very hard for them to be able to pull out just that, oh, it was the vaccine that was keeping them protected. And when they went to the wider studies, and when they went to the basically mandating it for everybody, when they started looking at those things for the populations, that's why the actual numbers started dropping down, because when they did that, people started going back to work, people started going out in public more often. It's like, so a lot of those other things that were keeping them safe started to drop off, and then you saw the true effectiveness of the actual vaccine piece. So that's how you really have to actually, when you're doing a designed experiment, you're looking for one very specific thing, and you have to make sure the experiment's designed to test for that one thing, and you can eliminate all the other possible outcomes and information from it. All right, let's look at a couple problems and see which we get. Vasectomies and prostate cancer. Yes, I just grabbed things from the book. So, so several studies have been conducted analyzing the relationship between vaccines or vaccines, vasectomies and prostate cancer. Dr. Giovanni, study leader, the epidemiologist of Harvard, said that we found 113 cases of prostate cancer among 22,000 men who had a vasectomy. This compares to a rate of 70 cases per 22,000 men who did not have a vasectomy. The study shows about a 60% elevated risk of prostate cancer for men who have had a vasectomy. But does this establish causation? So, first off, is the data that he has there descriptive or inferential? Okay. The data that's shown there is actually descriptive. So they didn't do a sample. They have all the data. Right? They know all the people who have vasectomies. They know all the people who have cancer. They were able to easily look at that actual data. So that's descriptive. The case where it starts to become inferential is, can we make that inference that, or that causation, that the vasectomy caused more cancers? Okay, that's where they're taking the descriptive piece, and that's where a lot of this stuff can kind of become a little fuzzy. Like that's where we're taking descriptive and now using this to show something else. Okay, that we might not have the data specifically on. Okay. They actually use this to look for cancer clusters and things. So if you have, and this is actually how they found the lead issue in Flint, Michigan, is they noticed a higher rate of and it was like heavy metal poison, but I can't think of the thing that lead actually does. Lower functioning things like that, because when you have lead in your body, it actually suppresses brain function. So they noticed a higher rate of that there than in other places, and they started to look at why this was the case. That's what they're looking at in this case, where they're looking at like, okay, this is a higher rate than everywhere else around it. It's like, what's happening here that's causing that to go on? And then they start to investigate. So they're looking at descriptive, because that's the data they already have. And then they're using that to start to infer and figure out what's going on in the actual situation. Folic acid and birth defects. So for several years, evidence has been mounting that folic acid reduces major birth defects. So that's descriptive. They're looking at data. They're saying there's evidence that this is happening. So these doctors, for the study, the doctors enrolled 4,753 women prior to conception and divided them randomly into two groups. One group took a daily multivitamin containing 0.8 milligrams of folic acid, where the other group received only trace elements. A drastic reduction in the rate of major birth defects occurred in the women who took the folic acid, 13 per thousand, compared to 23 per thousand to those women who did not. Is the study inferential or descriptive? This one's inferential. That's okay. That's the point. They did a sample. They did 4,753 women. They didn't do everybody. But then they took that and then they're inferring the information at the end. That if you were to look at this on a population-wide, women who took folic acid, it would be 13 out of 1,000 compared to 23 out of 1,000 for ones who didn't. So they're inferring that folic acid reduces the birth defects using that sample of 4,753 women. Okay. All right. Zillow.com is an online database. We've seen this. Most people probably have heard of this back in 2012. Apparently, people didn't. Here are some cities, the price per square foot, and some information. Is this data descriptive or inferential?
Descriptive.
That's descriptive because it's looking at all the information in that area. Okay, and that's actually one of the things that websites and databases and stuff like that can now do. Is it has access to all the data. So they can easily start pulling that information. And we're starting to see now with like AI and the ChatGPT and stuff like that, where they're actually looking at those are computer systems that are pulling all this data from everywhere and then starting to form inferences from that information. So they're not just spitting out the data. It's now saying, okay, this is what we think are happening, which is what we typically do. All right, we got the data, and now we're going to make some information, or we're going to make some decisions based on that information. So, all right. The Salk vaccine. We talked about vaccines. We talked about a lot. They used the polio vaccine a ton when they were saying, well, this is like the coronavirus vaccine and stuff like that. It's like the polio vaccine. Everybody's got to get it to protect us. So the Salk vaccine was actually not the first polio vaccine. I can't remember the name of the guy that did the first polio vaccine, but the first polio vaccine that they came out with was about 10 years before this, and it actually killed more people than it saved. So this was the most effective one that they had found, and this is the one that most people ended up getting. So in the test of the vaccine's efficacy involving nearly 2 million grade school children, half the children received it and half the children received the placebo. Neither the children nor the doctors performing the diagnosis knew which children belonged to which group. So that would be what's known as a double-blind study. A blind study means the participant doesn't know it. A double-blind means the participant and the doctors don't know it. Okay, that makes a difference because remember we were talking about before, it's changing behavior. When you look at a blind study, you don't change your behavior, but if your doctor knows, they might change their behavior. When it's double blind, nobody involved in the actual situation knows, so no behavior has changed. The researchers who are just literally getting data and have no interaction are the ones who actually know, but they don't have any interaction with you to change your behavior. The center found that the incidence of polio was far less among children inoculated with the Salk vaccine. So, was this an inferential study or a descriptive study? Huh? Inferential. Even though it involved almost 2 million kids, that's still a sample. That wasn't everybody. And this is actually the one that they made for general use. And if you ever look back at history or talked about it, you saw the lines of kids literally going into the nurse's office and getting the shots in school and everything else. So, all right. One more. Medical testing on animals. Yes, we do have to test some things on non-humans. Stated that 59% of Americans between the ages of 18 and 29 oppose medical testing on animals. The percentage of 59% was computed from sample data. All right, so let's identify some information because this is something we haven't actually really done yet. What's the population that they're talking about?
The ages between 18 and 29.
Yes, that's the whole population. Okay. Identify the sample under consideration.
Sample would be 59%.
Well, they're not necessarily asked 59%. The sample is that. So remember what we were talking about before when I looked at you guys compared to the whole school. Are you members of the whole school?
I'm a member, but I'm a member of the whole school.
Yeah, you are a member of the school, though, right?
Yeah.
So if I'm looking at figuring out the favorite color of the school, and I ask you guys were a sample of the whole school, but you're still a member of the population of the whole school. Your population and your sample has to be the same. The sample's just a sample of the population. So your population is people are Americans between the ages of 18 and 29. Your sample is a subsection of, or a randomized selection of 18 to 29-year-old Americans. It's got to be the same. If it's not the same, then you can't infer things. Like if I said the sample was 18 to 29 ages and the population was the entire United States, there might be a drastic difference between 18 to 29-year-olds and 59 and above you. So there's generational differences. So if I made my sample one group, this is what we're talking about with the polls, right? If your grandma is the one who's answering all the polls, they might not have the same views as you because you're a different population. So when you pick a sample, that sample has to be from the population that you're testing. Is the statement in quotes descriptive or inferential?
Inferential.
Okay. Why do you think it's inferential? Does it say that in the quote? No. You're right. It is inferential. But does it say it in the quote? No. So how would a general person who's not in Mr. Baker's statistics class who's going through all this, know that that was inferential and not an actual collection of all the data. They wouldn't. So what could we put in there that tells them that? What's on the bottom of every poll that you've ever seen on TV or in the newspaper or on the internet or anything else? There's something at the very bottom of every one of them. Normally not a scale, actually.
A citation to an actual website to which
Hopefully.
data was collected from.
Say like not X.
Nope. It says plus or minus 3%. Or plus or minus 3.5%. It'll say plus or minus some percent. That's how you know it's inferential. Okay? Because when you're looking at inferring something, and we're going to get into actual formulas and stuff like that in the next couple weeks. But when you're starting to look at inferring things, you have a range of error. Because when you're collecting data, you might not have all of the data. So you have a range that it's going to fall into, and that's at plus or minus 3%. Okay? So instead of saying 59% of Americans between the ages of 18 to 29 oppose medical research or testing on animals, it could say approximately 59%. Or 59% plus or minus 2%. Or based on a sampling of Americans aged 18 to 29, 59% say this. So there's ways to put that in there. They don't for a reason. Oh. So, all right. We are done. Stop recording this.